Hello and welcome to day 18 of learning ML from chatgpt. Let's get started. So yesterday we learned about Q tables. So this was the first lesson of reinforcement learning, where Q tables. So we had the state and the action. Then we had like a quality value to go with it. So it's basically the score. And then we had Q tables which had like loads and loads of different the state, action, and the Q value pairs. So yeah, and then we saw this example with the grid, and we're trying to go from one bit of the grid to the destination, which was the what was it called? Grid world. Okay, and then we saw that we could have an extra add-on bit to this, where we had a certain amount of Q values in our Q table, and after that, it can be much more computationally efficient in order to train a neural network on the current data we have, and then just estimate the values above, and then yeah, that's also a good solution. That's really interesting. So now let's go on to day 18's lesson. So please give me day 18's lesson. Let's see what we got for today. Okay. Deep reinforcement. Okay, so this is what we learned a bit about yesterday. Okay, let's see. Train and recurrent. No, sorry, not recurrent. Reinforcement learning model. Deep learning Q networks, DQN. DQN is a combination of Q learning and deep neural networks. It approximates the Q value function using a neural network, allowing it to handle environments with large state spaces. Key components include experience replay and target networks, which help stabilize training. Policy gradients. Unlike DQN, which learns value functions, policy gradient methods directly learn the policy, then mapping from states to actions. They optimize the policy by using gradient descent on the expected reward. Okay. So help stabilize. Common methods include reinforce and proximal policy optimization. So a good example, building a DQN in TensorFlow. Importing Gym, NumPy, TensorFlow, and Keras. Gym.make carpole. I don't know what carpole is. It's not really. So the assignment is to train a RL agent to play a simple game, carpole. Modify the provided DQN code to experiment with hyperparameters. Use different environments like mountain cart and lunar lander. Implement improvements such as prioritize experience replay or double PQN. Please explain this code. Okay, let's see if it can give us a better description of what's going on here. So yeah, this code implements a deep Q network to solve the classic carpole reinforcement learning environment from OpenAI's Gym. Okay, we're using OpenAI. Nice. I also heard recently that ChatGPT has a few new modes. Oh, let's see. It's got like 01 or something, but that may just be in the US. I'm not sure it's been shipped to the UK. Okay, let's try and get back on. GPT-4o, GPT-4o mini. Okay, no, it doesn't. Okay, so we're first importing. Okay, couple create Q model. TF.keras sequential. We're having 24 neurons as the input layer, with the activation function is relu. This if it's negative, it returns 0, and if it's positive, just returns it as it is. Input shape is the environment observation space shape. Then we're having another dense layer, and finally another dense layer with a linear activation function. Q network. This function builds a Q network which estimates the Q values, action value pairs. The input to the model is the state of the environment, the position and velocity of the car on pole. The network has 2 hidden layers with 24 neurons each, using ReLU activation function. The output layer has as many neurons as there are possible actions, 2 in car pole left and right. The output uses linear activation since we are predicting Q values directly. Hyperparameters. So gamma is how much the agent, which you saw yesterday, how much of a reward the future values are compared to like the current values. Close to 1 means long-term rewards are more important. Epsilon, the probability of the agent choosing a random action versus choosing the best known. Okay. Epsilon decay, the minimum value of epsilon ensuring the agent always explores a little. Batch size, memory. Okay, a relay buffer that stores past experiences. Okay, max memory size. Oh, that's how much is it? 100,000. Well, okay, models and optimizers. We're creating a model. Creating 2 models. Main target. The main Q network used to predict Q values. Target Q model, a separate target network to provide stable Q value targets during training. This helps improve stability. Set weights. The weights of the target are initially set to match the main model. Yeah, okay. Optimizer equals TF to Keras. The optimizer is Adam, as we've seen many times before. Learning rate at 0.01. So this is like for linear regression. I think it is like you change the gradient of the line by 0.001 every time. Optimizes the weights of the key network using Adam optimizer loss function, uses mean squared error. So this calculates it. So this basically just punishes outliers, and then used as mean, which calculates the difference between predicted Q values and target Q values. Experience replay. Okay, and then as a function that generates sample experience from memory to update. Okay, so this should just target the reward for taking an action plus the discounted max future reward if not done. The predicted Q values are updating using the Bellman equation. Gradient update. The gradients of the loss are calculated and the Q network's weights are updated via backpropagation. Training loop. Okay, so we're doing 1,000 iterations and we're just gonna train the model. Episodes. The agent is trained over 1,000 episodes. Each episode starts by resetting the environment. Environment will reset. Exploitation. The agent chooses an action based on the epsilon greedy policy. It either explores a random action or exploits the learned Q value. Action in step. The chosen action is performed in the environment. Random step action, which returns the next state, reward, and whether the episode is done. Memory storage. The experience tuple state action reward next state done is stored in the replay buffer. Experience replay. After each action, the agent trains using a mini batch of random experiences from memory. So if epsilon is greater than epsilon min, we do it. Okay. Decay. The exploration decays after each episode, so the agent explores less over time. And episode, if it's modulo 10, so it's so every 10, the weights of the Q network are updated. Of the target network, updated to match the Q networks. Stabilized learning, as it says. Episode total reward. Okay, in summary, this code implements a DQN agent that learns to balance a pole on a moving cart using a neural network to approximate values. Oh, I've seen this. I literally saw the actual animation of this before, and it uses experience replay and target networks for stable training. The agent explores the environment initially, but over time it relies more on learned Q values to make predictions. I'm just going to go to where. I'm just going to go back to this, add it, just carry on from this. Q learning algorithm, a popular RL algorithm to find the optimal policy. It works by updating Q value, quality value for each state action pair, which represents the expected future reward. the agents followed the policy. So where it goes to explaining the code. If we can get to the Q-learning agent. Okay. This section offers a Q-learning agent which learns how to act in the environment by updating its Q values. Okay. And so what was the alpha? That controls how much new information overrides old information. Okay. Gamma, as we saw before, the how much feature rewards are important. Epsilon determines the agent's likelihood of choosing exploitation, which is just picking like a path that's possible, or exploration. Oh, sorry, no, exploitation is when you know the best known one, but exploration is choosing just a random action that can be performed. Okay. And then updating the Q table, as we see there, and then training the Q agent. Okay then, so if we go here, let's copy paste the code into our environment. If I can get back to where we were. Okay. Now let's see if it works. It should work. It's just going to take a lot of time to train the model. Well, actually, yeah. Well, it's it's this type of model because it goes through a lot of well, this is using. We have got an error actually. With the code, I have the error. Now let's copy the original code. Okay, now let's see. The error you're encountering is replay buffer storing tuples of experiences. Okay, let's just okay. Let's see if this code will work. Okay, so this is the replay function that's being updated. Let's try run this. No? What? In batch. Setting an array element where the sequence requested array is a inhomogeneous shape after 2 dimensions. Let me see. No, I'll just go back to the top. Okay. Oh, this is slow. Okay, now. So now please provide the full corrected code. Oh no. Spelling, okay. Let's try and paste this to chatgpt. Okay, so okay, we're gonna keep with 4.0. Has it even started outputting or? Might have to resort to Bing in this case. The unlikely situation. Copilot. Okay, let's paste this code and tell Copilot to fix it. Please fix this code. Provide full code. Let's see if ChatGPT does it. Please fix this code and provide me with the full code. Okay, let's see. You couldn't output faster. Okay. I'm pretty sure that this Copilot is just ChatGPT. It may just be ChatGPT 3.5, but I don't know for certain. Okay, let's see. Supplying gradients, I'm not sure if they were present in the previous code. Okay, ChatGPT is also providing code. Just copy the ChatGPT 4.0, as I think it's just a larger model. That it is definitely a larger model and better model than ChatGPT 3.5. Okay, now let's try. Okay, let's see. I've got another error. Setting an array element is equal. Okay, it doesn't know how to fix it. So I'm just gonna leave the video there for now. I'll just try one last time with this. The Copilot. And see if this works. Let's see. Yeah, still same error. So yeah, I'll just leave it here for the video as we've learnt the content. So just to recap, it was just using. So we have some certain already Q values, the Q value table that we've predicted with a bunch of Q value pairs with the state and the action and the Q value, and then once we've got enough of them, we can train a neural network on these in order to predict future Q values, so that it'll be more computationally efficient, especially with really large data sets. So yeah, thank you for watching, and I'll see you in the next video. Goodbye. Oops. I'll just save this as a guest. Okay, thank you for watching, and I'll see you in the next video. Goodbye.